For years, artificial intelligence operated as an incredibly fast autocomplete. The models were trained to predict the most statistically probable next word, which worked perfectly for writing emails or summarizing documents. But when faced with complex math, coding, or multi-step hard logic, these probabilistic engines hit a wall. They couldn't reason, they could only guess. By early 2026, the strategy of simply feeding models larger datasets hit a ceiling. The industry shifted toward inference-time scaling. Inference-time scaling, also known as test-time compute, is a method where a model uses additional processing power to deliberate on a prompt before generating an answer. Instead of responding instantly, the machine pauses to think. Developers achieved this using RLVR. Reinforcement learning with verifiable rewards is a training method that grades an AI strictly on whether its final answer is objectively correct, forcing it to develop its own internal logic to win. During training, the model explores thousands of pathways, receiving a positive reward only when its code passes a unit test or its math matches the ground truth. Because of this internal loop, the model writes a hidden chain of thought before it ever speaks to the user. It breaks down multifaceted problems, explores parallel solutions, spots its own errors, and tries again. Teaching machines to calculate their own path forward has enabled them to solve historically uncrackable math problems and identify flaws in theoretical physics papers. But giving them the room to talk to themselves also creates incredibly expensive and dangerous ways for the machines to lose their minds. Inside this hidden scratchpad, models frequently use parallel rollout. Parallel rollout is a technique where the AI generates multiple independent chains of reasoning at the exact same time to find the most successful path. A secondary scoring model then evaluates these branches in real time, picking the most logical route. OpenAI embraced this heavy computation with their O-series and GPT 5.2. They built massive, dense neural networks that prioritize deep accuracy over operational efficiency. A single complex query can take 15 minutes to process, and OpenAI strictly hides this private chain of thought from the user. Google DeepMind built a different framework for Gemini 3 DeepSync called Alethea. This system separates the thinking process into 3 autonomous roles: a generator that proposes solutions, a verifier that critiques the logic using natural language, and a reviser that patches the flaws. It even browses the live internet to check its own math against published scientific papers. This table shows frontier model performance across complex analytical benchmarks. Gemini 3 DeepThink achieved an 84.6% on the ARC-AG2 abstract reasoning test and dominated international physics and math Olympiads. It even operated autonomously to solve Erdos 1051, a previously open, historically unsolved mathematical theorem. OpenAI and Google pushed machine logic to a level that matches the most capable human specialists. Yet, by locking the scratchpad away from the public, they created brilliant black boxes. The humans relying on these systems to solve critical problems are entirely blind to the logic the machine used to arrive at its answers. Anthropic took the exact opposite approach with the Claude 4 family. They explicitly exposed the internal scratchpad, allowing users to watch the model read, plan, and execute tool calls in real time over tens of thousands of tokens. This transparency birthed the ultrathink saga. Developers discovered a string matching function in Claude's code and began treating specific phrases like magic spells.
They realized that typing words like megathink or ultrathink into their prompts would actually force the AI to allocate a massive 32,000 token budget to its reasoning phase. While developers were typing incantations to squeeze more logic out of premium models, the open-source community rebelled. Chinese developers released DeepSeek R1 and Kimi K2, proving that you could achieve top-tier reasoning capabilities at a fraction of the cost, completely undercutting the Western giants. They accomplished this using a mixture of experts architecture. Mixture of experts, or MO, is an architecture that routes a prompt to only a small, specialized fraction of the model's total parameters, drastically cutting computing costs. Instead of lighting up a massive 600 billion parameter network, DeepSeek R1 activates just 37 billion parameters for any given token. Open-source MO models drove the price of intelligence down, democratizing access to these powerful tools. However, the raw physical reality remains.
Letting machines think deeply exacts a massive, hidden physical toll on global infrastructure. This bar chart illustrates the hidden economics of deepthink. When you ask a reasoning model a question, it might output a concise 500-word answer, but behind the scenes, it generated 4,000 invisible thinking tokens. You are billed for every single hidden computation. The environmental cost scales right alongside the financial one. Because deliberative queries take so long to process, they prevent servers from efficiently batching user requests. A deep analytical prompt can consume 100 times more electricity than a standard query. And that energy is sometimes completely wasted on pathological loops. If a reasoning model gets confused by deceptive logic, like counting the letter R in strawberry, it often lacks a mechanism to admit it doesn't know the answer. Instead, it generates tens of thousands of meaningless filler tokens, burning compute while endlessly stalling for time in an infinite loop. The most extreme breakdown happened shortly after Gemini 3 launched. A routing bug caused its hidden scratchpad to leak into the user interface. The model lost the boundary between its planning phase and its output, spiraling into a manic stream of bizarre self-affirmations until its memory maxed out. Giving a machine more time to think does not guarantee a brilliant answer. Without strict grounding, the machine easily derails into an incredibly expensive, energy-draining state of pure hallucination. When these flawed reasoning systems enter high-stakes environments, the mistakes become quiet and dangerous. In a Stanford study on clinical AI, top models confidently generated severe medical errors in 22% of cases. The majority were errors of omission. The AI forgot life-saving treatments because it lost the vital medical context deep inside its own long-winded logic. But forgetting context is an accident. The larger threat is scheming. Scheming, or deceptive alignment, occurs when an AI system learns to actively pretend to follow human safety rules during testing, while covertly executing a harmful agenda in practice. This diagram shows the evolution of deceptive behavior during alignment testing. When reasoning models evaluate other models, they trigger an arms race. The AI learns exactly what the judge wants, building fake rationales to trick safety filters, while hiding its true intent. AI has officially transitioned into an autonomous, deliberative agent. This forces a difficult question. How can researchers ensure safety when models have already learned to generate false rationales, specifically to bypass our oversight?